All right. So, what we've been doing here, whenever we see that limit that we've been doing here, okay, evaluating that, okay, we have a lot of different names for this thing. It's like a difference quotient, right? Well, not a lot of names, but that's the name we have for it. I guess it's a difference quotient, right, when we evaluate something like that. And it has a meaning in calculus, okay? It's how we find the slope of a tangent line, or the rate of change, or the slope of a function, okay? That's what we use that for. I don't think I showed you guys like where that comes from, but you can kind of see the slope formula in it. You know, for example, here if we think, you know, okay, there's kind of like a y2, right? Because a function value is like a y value minus another y value over, and then there's our x2 minus x1, right? So it's like f of x, and then minus an f of x there, and then there's our x minus our x there. So this is kind of like a slope formula, basically, because this then simplifies, as you can see there, to the x's cancel out, you're left with the h. So that's why you get that kind of slope formula there. Okay. So we use this to find the slope of a function at a given point. And that, you'll get more into that in calculus, and we may get into it a little bit ourselves here, but I don't want to go too much into the conceptual stuff right now just because, I don't know, I feel like that's, you know, maybe not as important right now for us, since you're not taking actual calculus, you're just doing pre-calculus. Okay? So, what we're going to do then is kind of jump right into what I'm going to call basic differentiation rules. And the differentiation, by the way, that means just it's the process of taking or finding the derivative. Okay, so kind of two vocabulary words, right, that we haven't really talked about too much. The word derivative, the word differentiation, right? Okay, and the derivative is simply this limit that we evaluate here. This specific kind of limit when it's a difference quotient and it's the limit as h approaches 0 of that difference quotient. That's the derivative. Okay, and it has meaning and a purpose in calculus and in mathematics, I guess, in general. Okay, but right now we're just going to focus on how to evaluate this limit without having to evaluate the limit. Okay, how to get the answer for this thing without actually having to evaluate it. All right, so we're gonna start with basic stuff, and we'll kind of work our way up to more complex things today. So the first thing we're going to look at is the constant rule. Okay, so look at that first. Okay, so we're going to start by, we'll use the definition of the derivative. Okay, to find the derivative of y equals 7, or f of x equals 7, if you please, you know. So we use the definition of the derivative to find the derivative of y equals 7. Okay, so again, what is the definition of the derivative? Well, again, it's that limit. It's this specific limit. That is the limit-defined definition of the derivative. The way you define the derivative using the limit definition. So that is the definition of the derivative right there. Again, what's the idea behind the derivative? It helps us find the slope of a function at a given or any specific point. Now, you guys, believe it or not, can evaluate this derivative of this function right now mentally without having to go through this limit. You all know the answer to this is. Okay, and I'll show you how you know that. So if we go and if we look at the graph of this thing, which you guys don't know what it looks like. You don't need to pull out your graphing calculators necessarily, but I'm going to pull mine out just so you have it. Okay, there it is, right? Y equals 7, the graph of that is this horizontal line. What is the slope of a horizontal line? 0, right? So therefore, the derivative, which is supposed to describe the slope of your function along at any point, well, since the slope of this thing is always 0, then the derivative of 7 had better be 0, right? It's constant. It doesn't go up or down. It just stays flat the whole time. So we should get an answer of 0 here. And so let's see if we do end up getting that. Okay? So y equals 7 really just means that f of x, right, is equal to 7. Right? That's the same idea there. F of x equals 7. And so if f of x is equal to 7, then what is f of x plus h going to equal? What's f of x plus h going to equal? This is not a trick question. 7! Yes, 7 again. Exactly right. It's going to be 7. Okay. Because there's no place, right? There's no x or anything over here. There's no variable we have to like change around. So if f of x is 7, that means just f of x plus h will also be 7. So we're going to end up with the limit as h approaches 0 of 7 minus 7 over h. Right? F of x plus h, that's 7. F of x is 7, and so we end up with 7 minus 7 all over h, which then, if we simplify that, 7 minus 7 is 0. Right. And what's 0 divided by h? What does it simplify to? It's 0. And so now we're taking the limit as h approaches 0. 0 divided by h, that h is gone. You took 0 and you're dividing it by h. It's just 0. And so the limit as h approaches 0, there's no more h's in there. So the answer is just 0. It's just 0. Okay. And of course, this is going to be true for any number, right? Anytime we have this, like y equals a number, so like y equals 5, 10, negative 100, whatever you want to say, okay, pi, right? Pi is a constant too, pi is a number. Its derivative, okay, its slope should be 0 at any point because you're going to have a horizontal line, and a horizontal line always has a slope of 0, right? And so that's true in general. So the constant rule so that was just an example, and now we're actually going to define things here. Is that if a constant function, so your function is just equal to a number, is differentiable and differentiable, again, is a term that you will learn about, like, what that means. It basically just means able to be differentiated. And you'll talk about, like, when things aren't able to be differentiated and stuff like that. That'll be more in calculus, but I still want to give you the official definition here. So, so again, the constant rule is that if a constant function is differentiable, then the derivative of that constant is 0. The derivative of that constant is 0. And symbolically, using calculus symbols, that's how you write that with calculus symbols. The derivative of c with respect to x is 0. Okay. And of course, over here, c is a real number. Okay, so there's our constant, right? There's our constant c. If we take the derivative of that c, it should be equal to 0. Okay. Again, don't get hung up too much on what the idea of differentiable is. Don't get hung up too much here on the these symbols and stuff like that, what those all mean. Okay, I'll write it up here too. Again, how you read this. the derivative of c with respect to x is 0 or equals 0. Okay, that's how you read that. The derivative of c with respect to x is 0. And the idea that with respect to x part is just the idea that you can have multiple different kinds of variables. You can have different variables in your function, right? We don't always have x's. Sometimes we have t. Sometimes we have, you know, m, n, p, whatever it might be. You're not always going to differentiate with respect to the variable x. Sometimes you want to differentiate with respect to the variable, you know, m or t or whatever you've got in your problem there. Okay, so that's the idea. Okay. And so, for example, if I had okay, let's just say, for example here, let's say I wanted to find the derivative of f. If I have the function f of x equals, I don't know, 10, okay, what would the derivative of 10 be? The function is equal to a constant here. So what's it going to be? What's the slope of, if you graph this, y equals 10, if you graph that, it would be a horizontal line through 10. And so the slope of that anywhere would be what? 0, right? So this is 0. Okay? But of course, I don't want to just say equals 0 like this, because that's implying that f of x is also equal to 0 then, right? I did like f of x equals 10. That's the function that's equal to 10. How do I denote the derivative? Well, the way you write the derivative is actually pretty simple. It's just the f again, but you put a little apostrophe up here like that. That's called f prime. F prime denotes the derivative of f. Okay. So rather than going through all that mess, all this mess here with the limit definition of the derivative, rather than doing that to f, we just use this constant rule. The constant rule says that if you take the derivative, if you try to evaluate, if you do the definition of the derivative to a constant, it gives us 0. Okay? And so I'll do another one here. How about f of x equals, you know, negative 27. Okay, what would f prime of x be here? It would be what? It's equal to a constant. So what's the derivative of a constant? 0. Okay. How about one more here? F of x equal to e. What's f prime of x going to be? Here's the graph of f of x equals e. What's the slope at any point on that line? 0. Yeah, it's a constant, right? Don't get thrown off the fact that e is a letter, right? Yes, we know. Most of the time when we see a letter, we're thinking of variable, and so maybe we pause. Remember, e is specifically the number e. So e is this number. Taking the derivative of a number, you get 0, okay? All right. Bless you. So there's that, okay? There's like one of our rules. Again, the constant rule, okay? The constant rule there. But what about if we don't have a constant, right? Because there's tons of other stuff we've worked with before that doesn't necessarily have, you know, or it's not a constant, okay? So now let's get into something called the power rule. Okay. And we're going to actually, you know, figure out the power. I'm going to give you guys an opportunity to figure it out, I'll say. Use the definition of the derivative. Which again is that limit as h approaches 0 of f of x plus h minus f of x all over h. Okay. That's the definition of the derivative. You're going to use that, okay, to find each of the following. So we'll do a couple of these here, and hopefully you'll get the hang of what's going on. We'll do, well, I guess 2. Okay, we'll do 2 here. We're going to do 3, but, well, we've already done one of them. So, for example, g of x equals x squared. Okay. We'll say g of x equals x squared. Just using a different function name, that's all. Okay. And so we're going to evaluate this. Let me go ahead and just make that f. Sorry, I'll just keep it f, just to keep things from being confusing. Make it f instead. All right. Well, we just did that for the warm-up, right? And so rather than going through all that all over again, maybe I'll set up like the first part. So that's like the limit as h approaches 0 of x plus h squared minus x squared all over h and dot, dot, dot. We did all that work already, so we're not going to like do it all over again. We end up with 2x, right? We end up with 2x here in the end. F prime of x equals 2x. Now that's weird. Earlier, when we were doing these, right? When we found the derivative of f of x equal to 10, we end up with 0. And that kind of made sense, right? Because again, if we graph 10, okay, it's a horizontal line right there at the top. It's like it's just in there, right? So the slope along there at any point is 0. X squared, though, when we graph that, the slope here, what's the slope of this thing? It's a curve. If we try to find the derivative of this thing, try to find the derivative of x squared, the slope doesn't really make a lot of sense necessarily because it's curved, right? It's not flat really. But we should have kind of an idea about the slope here, about the derivative here. I mean, for example, if I asked you for the slope, because the slope's kind of changing, right? I mean, it looks different on this curve. But if I asked you for the slope at this point right here, what might you say the slope is at that exact point? At this precise point, you might think the slope would be what value? 0. Yeah, okay. Plus, what are the slopes here? Any slope along here, right? If I like take my little pen here and I kind of put my pen along there, right? Any slope along here, what would the sign be of that slope? Would it be a positive slope or would it be a negative slope? Positive, right? Because it's going up from left to right, right? My pen here, if you look along that line, all the little slopes are going to be positive. What about this left-hand side here? What kind of slopes would you expect here? Positive slopes, negative slopes, 0 slopes? Negative, right? Because again, if you look, think about my pen here, right? It's going down as you go from left to right. Okay, right? The slopes that would line up with that would be going down. And then again, right at the point where it changes from here to here, right at kind of the trough there at the very bottom, right? It kind of bottoms out, and we have a flat line, and then it kind of starts going up again. So we go negative slope, negative slope, negative slope, negative slope, negative slope, 0, and then positive slope, positive slope, positive slope, positive slope after that. Okay. So in other words, the slope is changing. So it makes sense then that our thing that we're using to describe the slope, our derivative, okay, it changes depending on where you are, your x location. And in fact, it kind of matches here, right? Because what's the x value at this point where we say the slope was 0? What's the x value there? What's the x value at this point right here? It's what? 0, okay? And if you look down here, right, if I plug 0 in for x, 2 times 0 would be 0, and it gives me a slope of 0 there. If I pick any point to the right of 0, if I pick any x value here to the right of 0, any x value here, it's going to give me a positive slope value, right? So for example, if I pick 1, 2 times 1 is going to be 2. So the slope at this point right here, where the x value is 1, that slope is going to be 2. Okay. If I go to the left, I pick any x values to the left of 0. So for example, I don't know, like negative 3. Okay, there's negative 3 right there. If I go up, that should be a negative slope. And sure enough, negative 3 times 2 is negative 6. So we get negative 6 slope there. Okay, so this thing, when we take the derivative there, this thing that we get, this derivative, okay, it describes the slope at any point on our function, but of course it's changing, so you have to put the x value in for whatever point you're on and stuff. Okay, there's that one. All right, let's see here. Let's do another one. How about f of x equals x cubed? All right, I'm going to help us out with this one too, because that's a bit much to have to evaluate. So let's find the derivative of f of x equals x cubed. All right, so this is going to be the limit as h approaches 0 of x plus h cubed minus x cubed all over h. And of course, to cube this thing out, x plus h times x plus h times x plus h, it's a lot of work. I'm going to go ahead and just jump that, though, and give you the simplified version of it. So it's going to become x cubed plus 3x squared h plus 3x h squared plus h cubed minus x cubed all over h. Okay. So again, I went ahead and just multiplied that out. Kind of skip some steps there, just so we can do this quickly. Okay. And so we have the x cubes, they cancel out in the numerator there. And so we're left with the limit as h approaches 0 of 3x squared h plus 3x h squared plus h cubed all over h. But again, we're kind of stuck here, because if I plug in a 0 right now, if I plug in h equals 0 right now, I'm going to have 0 plus 0 plus 0, so 0 in the numerator, all over 0, so I get indeterminate form. But what can we do here for our next step to kind of help simplify? What can we do for our next step here to help us proceed? What can we do? Listen. Factor out an h in the numerator, exactly right. Okay. So it's h times 3x squared plus 3xh plus h squared there. Okay. The h's will cancel. And so we're left with this. Which now, when we evaluate that limit, what will it equal? What's going to be left over when I plug 0 in for h? What's left? If I plug in 0 for h, what's now going to be left? What remains? Yeah, 3x squared, and that's it. So the derivative f prime of x is 3x squared. Okay, so let's kind of review here. X squared goes to 2x, right? The original function x squared goes to f prime equal to 2x. The original function x cubed, when you take the derivative of that, becomes 3x squared. All right. Do one more here, and we'll see if we've got it. Maybe some of you guys have an idea already about what's going on here. Maybe not. It's okay. Let's do one more here, and again we'll say f of x equals the square root of x. Okay, so do one more derivative here. The hard way, the long way. One more derivative the long way. Okay. So, square root of x is not very helpful for us, but of course we can rewrite the square root of x as x to the what exponent? X to the 1/2. That's right. Okay. So let's take the derivative of this. All right. So it's the limit as h approaches 0 of, I'm going to go ahead and just substitute in here, x plus h to the 1/2 minus x to the 1/2 all over h. Okay, so We're going to use that limit definition of the derivative, and there's how we'd set that one up. Okay. To do a problem like this, right, we're kind of like, before we could like actually cube out that x plus h, or here we could actually square out the x plus h. But here to square root x plus h is not really something we can like do. Okay, we can't distribute the 1/2 to the x and the h, right? Just like we couldn't distribute the 3 to the x and the h, or the 2 to the x and the h like that. It's got to be the square root of that sum there. We can't break it up like that. So to evaluate this limit, we have to go back to an old strategy of multiplying by the conjugate. So we'll multiply by x plus h plus x to the 1/2 over x plus h to the 1/2 plus x to the 1/2. So we're going to multiply by 1, but we'll multiply by 1 in a tricky kind of way there. And when I go and multiply this numerator together, right, kind of think of it like a binomial, right? So we have to do like first, the outer, the inner, and then the last, right? So if I multiply these two first terms together, maybe I'll zoom in some more here for us too. When I multiply these two first terms together, it's going to be an x plus h to the 1/2 times an x plus h to the 1/2. Same base, right? X plus h and x plus h when I multiply those together. So same base, I'm going to add the exponents, which is 1. So it becomes just the limit as h approaches 0 of x plus h, that quantity, to the 1, or just x plus h, right? Anything to the 1 is just that. So we multiply the first things together. We got x plus h. Now we multiply the outer. We'll have a positive x to the 1/2 times x plus h to the 1/2. But then the inner will have a negative x to the 1/2 times x plus h to the 1/2. So what's going to happen to that middle term? It cancels out, right? And so we go to the last term then. Negative x to the 1/2 times positive x to the 1/2 will become negative, and x to the 1/2 times x to the 1/2 is x to the 1, or just x. Right? All over, and then we still have to do this. I'm going to leave the h. I'm not going to distribute the h. I'm going to leave the h unmultiplied here. So I'm just going to do the x plus h to the 1/2 plus x to the 1/2. Wow. So the numerator here, the x's cancel. We're left with just h over, and then h times x plus h to the 1/2 plus x to the 1/2. And the h's cancel too now. And so finally we're left with the limit as h approaches 0 of 1 over again, just canceling out the h's there, right? They cancel. So after 1 over the quantity x plus h to the 1/2 plus x to the 1/2. And now you can finally plug in 0 for h. We can finally plug in 0 for h. And x plus 0 is just be x. So we x to the 1/2 plus another x to the 1/2. And so we have really 2 x to the 1/2 there. So it's 1 over 2x to the 1/2. Because they're like terms, so you just add them up. And then to help us out here, okay, so again, because it might not be so obvious, right, we like, maybe you guys like looked at the back at the x squared here, and you're like, oh, okay, I kind of see something happening here. And you're like, x cubed, and maybe you kind of like, I kind of see something happening here too, maybe. But then you might look at this, and go from x to the 1/2 to this. I'm like, I'm not really sure what's happening here. But let me rewrite it just a little bit more. Okay. Okay. So 1 over 2x to the 1/2 is the same thing as 1 over 2 times 1 over x to the 1/2, right? When you multiply, you just multiply across the top, multiply across the bottom. And I'll do one more change here. Instead of 1 over x to the 1/2, let's make it 1/2 times x to the negative 1/2 like that. And so we go from x to the 1/2 to 1/2 times x to the negative 1/2. All right. So does anyone want to take a shot here at trying to describe what's happening when we take the original function, x squared, or x cubed, or x to the 1/2, and then go to its derivative? What's really happening here? And it might be helpful if I write this in here as well. What happens? Or what can you see happening here as we go from the original function to its derivative? Anything you see, anything you notice happening? When I take x squared, I take its derivative, I go to 2x to the 1. When I take x cubed, x to the 3, its derivative is 3x to the 2. When I take the function x to the 1/2, its derivative is 1/2 times x to the negative 1/2. What's happening? Yeah.
You multiply it times the original exponent and then subtract 1.
And that's the power rule. That's the power rule. Exactly right. Okay? Your original power multiplies out front, and you lower the power by 1. Original power goes out front, and you lower the old power by 1. So 3 goes out front, and then comes x squared. It even works here. X to the 1/2. The 1/2 goes out front, there's the 1/2, and lower 1/2 by 1. What's 1/2 take away 1? Negative 1/2. Okay? And so that is the power rule. Okay? So here it is. The power rule is if n is a rational number, okay? If n is a rational number, rational, so that means it's like a fraction, right? So like, you know, x to the pi, we're not going to talk about taking the derivative of that right now, but x to the 3/4, we could do that. Okay, if n is a rational number, then, and, so again, the power rule is if n is a rational number and f of x equals x to the n is differentiable, then f prime of x, the derivative, right, of f, equals n times x to the n minus 1 power. Or again, in calculus terms, good day, sir. Yeah, why not, right?
All right.
Yeah, thank you.
Enjoy.
Yeah, I will.
Well done.
Yeah, well, I'm just like, might as well, right? Do some actual calculus.
What does that mean? You've done polar parametric?
Yes.
And it's not in series?
Yes.
Cool.
Yeah.
All
So
right.
we'll talk, because I forget when we said we were going to do the benchmark.
I remember.
Yeah.
I have those things left to do.
Yeah.
Enjoy.
Right, yep, we'll see you. He was out for a week in Texas, too, so that's why. Okay. So anywho, the derivative of x to the n is n times x to the n minus 1. Okay? And that's our rules. Alright. So let's use this now. Rather than going through this whole mess of like the limit definition and stuff like that, let's use this instead to find the derivatives of some things. Okay? To find those slopes. Okay. All right. So, for example, here, okay. I guess I'll put a little EX here. Let's see. g of x equals x to the 4. So then g prime of x is going to equal what? Done? Cassie, what do you say? Same thing. And they're both exactly right. 4x cubed. Yes. The new power, or sorry, the old power 4 goes out to the front, becomes your coefficient, and then the new power becomes x cubed. Okay? Let's try another one here. By the way, we can also take like multiple derivatives, right? So like you can talk about the first derivative, but there's also the second derivative, third derivative, so on and so forth. So we can actually take the derivative again here. If I wanted to find the second derivative, which is denoted g prime prime of x, okay, I want to take the second derivative here. Anyone want to guess what the second derivative would be? Yeah, Nick?
12x to the 11.
12 x to the, your old power was 3, so just lower it by 1. It'll be 2.
So, yeah.
Just 2.
Alright.
Like that. You see it there now? Yeah. Okay. Yeah, that's right. And you keep going. You can keep going, of course, obviously. All right, let's try another one here. How about the cube root? Cube root of x. The derivative of the cube root of x. Of course, the way this is written may not be very helpful, but let's rewrite it as x to the what exponent? Cube root of x is the same thing as x to the what? 1/3, right? And so then its derivative would be what? Cassie. So 1/3 times x to the, and then 1/3 take away 1 is not negative 1/3. 1/3 take away 1 is negative 2/3. But right idea though. Right idea. Yeah. I know fraction arithmetic. Not everyone loves that stuff, right? All right. Do one more here. How about, I don't know. We'll do like k of x and say 1 over x squared. Okay. Tell you this. It does not equal that. Although it does not equal there. Okay? Does not equal that. But let's rewrite this. 1 over x squared is the same thing as x to the what exponent? Negative 2. Okay. And so if we want to find the actual derivative here, well, you do the same thing. You take that negative 2, bring it out front. So it's going to be negative 2x. We have to lower our exponent by 1, so it's now negative 2x to the what power? Negative 3. Okay, so it's actually negative 2 over x cubed is what it ends up being. Okay, like that. Yeah, Cassie?
Can you leave it the first way, or like...
This way?
Yeah.
Yeah, that's fine.
Okay.
Right. Yes, 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 yes. You can leave it that way, yes. Okay. So there's that. There's one other little rule I want to talk about, and this one's not, we're not going to like derive this or anything like that. We're just going to find one more here. It's called the constant multiple rule, and then I'll let you guys get started on the assignment here. Okay. And so basically, the constant multiple rule is this. If is a differentiable function, so again, if f is a differentiable function, okay, and c is a real number, then, okay, so if f is a differential function and c is a real number, then I'm going to use the symbols here. The derivative with respect to x of c times f of x is equal to just c times f prime of x. Okay. Which means, just as an example here, for example, if I have g of x equals 3 times x to the 4th. Okay, if I have g of x equals 3 times x to the 4th, right? And this is something that, you know, we already kind of looked at a problem like this earlier when we took the derivative again. All right. Right now, we only know, according to like our power rule, we only know how to take the derivative of x to the 4th. We haven't really talked about taking the derivative of 3 times x to the 4th, right, when there's a coefficient in front here. But the constant multiple rule basically just says that you can just take the derivative as if it's just x to the 4th and then multiply back by that 3 again. So the 4 would still come out front, right, when you take the derivative for g prime. It'll be 4, but then there's the 3 there, so it's going to be 4 times 3, which is 12. And then you lower your power by 1, so it's x to the 3. That's the derivative, that's all. So the 4 just comes out front, multiplies with the 3, and 12x to the 3rd. That's all. Okay. And I want to do, sorry, I said one more, but I forgot I want to do. Also the sum and difference, too. I just want to talk about that as well, because that's pretty straightforward, too. Okay. And this one I'm just going to use symbols for. So for the sum difference rule, so again, what happens if we have addition? What happens if we have subtraction? The derivative with respect to x of f of x plus or minus g of x. So again, I'm being kind of lazy here. I don't want to write two different rules because it's the same thing. So it's if you add them together or if you subtract them, either way, it's just equal to f prime of x plus or minus g prime of x. Okay. So if you have two things added together, you can take their individual derivatives and add those back again together to get, you know, what the ultimate derivative is. Okay. If you have two things being subtracted, two functions being subtracted, then you can find their derivative by just taking the individual derivatives and then resubtracting them. So as a quick example here, bless you. If f of x is equal to something like x cubed minus 4x plus 5. I'll go ahead and just make it 4x to the 1 plus 5. Okay. Again, this is different than the ones we've done in the past. In the past, we only had one term. Here we have 3 terms we have to deal with. But you just take the derivative like normal. So, f prime of x is equal to the derivative of x cubed is what? What will it be? Anyone? 3x to the 2, or x squared. Yep, good. And then 4x to the 1. Well, the 1 will come out front, becomes minus 4. X to the, take away 1 from that, it's going to be 0. And then what's the derivative of a constant? 0. Okay, so we're left with 3x squared minus, x to the 0, remember, is just 1, so it's just 3x squared minus 4. And so there's your derivative. Alternatively, right, we could take this thing and put it in the limit definition and simplify that limit down, and you get the same thing, 3x squared minus 4. All right, so that's that. Let me give you guys your assignment here.